Hello everybody, and welcome to the second video in this series. And today I will be talking about algebra and looking at some of the basic topics in this branch of mathematics. Algebra is the branch of mathematics that deals with how different quantities are related to each other by means of non-numerical symbols. In this tutorial, I'm going to give a brief introduction to solving the most common type of equations that you will encounter in physics. I'm going to start on reviewing the most basic one-variable type of equations that we encounter. Then I'm going to move on to single variable quadratic equations, where I will summarize how to solve this kind of equations. Then I'm going to give a simple introduction on how to solve linear systems of equations of two variables and give an insight on how to solve more complicated systems of equations with two variables. Finally, I'm going to give a brief overview of inequalities. And as the final remark before starting, the part on solving linear equations is a very interesting topic since it appears everywhere in physics when implementing mathematical numerical methods, even for nonlinear equations. So if I have enough time in the not so near future, I will try to make a tutorial completely dedicated to linear algebra, that is the branch of algebra that is dedicated to solving this type of linear equations. So well, let's get started. So algebra is probably the first real practical, useful, and fundamental topic in physics. And well, since algebra is a branch of mathematics that studies the behavior of relations between different variables, it is the start of very interesting topics like functional analysis, differential equations, and a bunch of other topics. Also, algebra will be useful to us in physics, since physics is a science where we want to know how different quantities relate to each other quantitatively and thus be able to build a model that predicts the behavior of a system within an adequate framework. So we will start with the simplest operation or algebraical procedure and gradually progress to more difficult topics. So let's start with something basic. So imagine that you have the simple operation 7 plus 3, that of course equals 10. It turns out that most of the time in real life, we are not given all the information that we require to solve a problem, but most of the times we have almost all the information. Call this black box X, and we want to know what the value of X is. And since this is an equality, we can subtract 7 from each side. So remember, since this is an equality, we can do whatever to the equation, and as long as the operations are made to both sides of the equation, it will remain an equality. In our case, if we subtract 7 from each side, and well, 7 minus 7 is 0, we can set them to 0, and on the other side, we know from the algorithm of subtraction that 10 minus 7 is 3, leaving x by itself on the left side of the equation, and 3 by itself on the right side of the equation, concluding that for the equation to be consistent, x must be 3, as we expected. So the previous equation is as simple as it can get in terms of solving for an unknown variable, and solving these simple equations is pretty straightforward. Another example, you have the equation 8 plus x equals 23, and you want to solve for x. You can simply subtract 8 from both sides to solve for x, concluding that x in this case is 15. So solving for x just means to isolate x in a side, either left or right, by means of the elementary operations of the number space in question. Just as a reminder, we are working in the number space of the real numbers. So let's level it up a little and say that the equation now reads 8 plus 3 times x equals 23. So now the question is, how do we solve for x? Let's start by subtracting 8 from each side, such that we get that 3x is 15. Notice that we now have a very simple equation that we can simply solve. This is achieved by dividing both sides by 3, and noticing that 15 divided by 3 is 5, concluding that the value of x for this equation is 5. To check that our answer is the value we're looking for, we replace 5 as the value of x in the original equation, and after performing the addition and multiplication operations, we see that the result is 23 as we expected. So now that we have taken a look at simple equations, I want to move on to a slightly more complicated type of equations, the quadratic equations. So let's make things more interesting. Assume that you have an equation where you want to know what number multiplied by itself or the number squared yields 4. From the usual multiplication algorithm, and if you know your multiplication tables, it turns out that the value of x you are looking for is 2, and you can check it by replacing x by 2 in the equation, and it turns out that 2 multiplied by itself does yield 4. But wait, what if x equals minus 2? You can replace this value in the equation, and again, using the laws of multiplication, you determine that minus 2 squared is also 4. Thus, we conclude that the values that satisfy the equation x squared equals 4 are plus and minus 2. So notice that quadratic equations can yield 2 values, whereas a linear equation only gave us one solution. Now, how about if we want to find all the numbers that multiply by themselves yield minus 4? The answer is that we cannot do this, at least not for the numbers we are dealing with, that are the real numbers. So we conclude that there are no solutions in the real numbers to this problem. Let's now make things somewhat more complicated, such that we want to know what values of x satisfy the equation 2x squared plus 3x equals 1. Is it possible to solve this equation? The answer is yes, but it is more complicated. Before continuing to solve the problem, it is convenient to define a very important element in algebra, and it is that of a polynomial. A polynomial of order n is a sum of integer positive powers of x, where the coefficient of x to the n is non-zero, and any coefficient of x to a power greater than n is 0. For example, if we define a polynomial of order 7, notice that the coefficient next to x to the 7th power is 5 or non-zero, and the other powers of x are positive or 0, and less than n, but not negative. Another reminder is convenient. When multiplying, say, two order 1 polynomials, you can use the distributive property to multiply term by term and obtain a second order polynomial. That, as you can see, in general, can be expressed as the product of two 1 order polynomials multiplied by a coefficient alpha that depends on the leading coefficients of the x's in the 1 order polynomials. Notice also that if you replace x by x1 or by x2, it will yield 0. Unfortunately, we cannot always find x1 and x2 in the real numbers, so at least in the context of the real numbers, the polynomial cannot always be factored. Going back to our problem, we have an equation where we want to find out the values of x, where 2x squared plus 3x is 1. Solving this equation in general is not trivial, but it can be solved. Let's first rearrange the equation to an equivalent way by subtracting 1 from each side, such that the equation now reads 2x squared plus 3x minus 1 equals 0. So put it another way, we want all the values of x that when replaced into the expression 2x squared plus 3x minus 1 yields 0. And there are 4 ways that this can be done. It can be done intuitively by knowing your multiplication tables. You can try and factor the polynomial as you did in school. You can use numerical methods that are the numerical routines used by scientific software, like the Newton-Raphson method, numerical algorithms like that. You can also do it graphically. That is an interesting idea, and that we should take a look at. And there is the flawless method for second order polynomials, that is to find the roots using a formula. That is the other method we will also explore. So, as I said, we will be exploring 2 methods. The first method is the graphical method. The problem again is to find all the values of x such that 2x squared plus 3x minus 1 is 0. The strategy to follow is very simple. We first take a few values of x and calculate the values of the polynomial at those values of x. Call these values the y values. We then draw a chart that has a horizontal line that we call the horizontal or x-axis, on which we define equidistant points that represent consecutive and equally spaced values of x. We then define a vertical line that we call the vertical y-axis that will represent the values that the polynomial can take. And again, we set equidistant points along the line that represent consecutive and equally spaced values that the polynomial can take. After that, for each value of x, we can draw dots at a vertical position such that these dots represent the value that the polynomial takes for that specific value of x. Notice that in general, for each value of x, there can be more than one value of y. But in our case, for each value of x, there is only one value that the polynomial can take. This approach is called graphing. And you might want to take more values of x, but notice that we can only choose a limited amount of values. We cannot really get the values for every value of x, since doing so would be impossible, right? Since we would have to consider all the rational and irrational numbers in the interval we chose. That is just not possible. But by choosing a few points, we can kind of draw a line that would, at least in principle, fill in for all the missing values. Now, to solve our problem, we are looking for the value or values where this curved line we have just drawn intersects the horizontal line, since at this line the polynomial has the value of 0. That is what our equation is asking for. And we notice that the values of x where this curve intersects is when x is approximately 0.20 and there is another intersection when x equals roughly minus 1.8. Of course, the interval of x values we have chosen to graph needs some intuition, but that intuition has to be trained by practice. But, well, let's see how close we can get when using the formula. So the next method I want to focus on is where we solve the equation to get the values. So instead of having to use numerical methods, intuition, or even graphical methods, we can just use a simple formula called the quadratic equation solution formula. So let's first set the equation in what is called the standard form. In our case, the standard form of the equation is required since it is the way in which the coefficients in our solution to the equation will be defined. In our case, the equation to be solved is 2x squared plus 3x minus 1 equals 0. And I'm not going to go into the details in how to get the formulas, but on how to use them, since getting to the result is quite cumbersome. The fact is that there are two solutions to the quadratic equation, and they take the form x1 equals negative b plus the square root of b squared minus 4 times a times c, and that result divided by 2 times the value of a. The value of x2, or the second solution, is similar, but instead of adding the square root to negative b, it is subtracted from negative b. And just as a side comment, and before continuing, it is important to remember that for a polynomial of degree n, there are exactly n roots or n values of x for which the polynomial is 0. This fact is called the fundamental theorem of algebra. So for a polynomial of degree 2, there are at least and at most 2 values of x that yield 0 for the polynomial. So to get the values of x1 and x2, we get the values of a, b, and c, and in our case, a is 2, b is 3, and c is minus 1. So we first get x1 by substituting the values of a, b, and c into the formula for x1 that turned out to be 0.28078, and for x2 we get that it is minus 1.7808, and both values are given to 5 significant figures. So let's look at another example on how to use this formula. Say we have an equation of the form x squared plus 1 equals to 0. That is, we want to find the roots of this polynomial or the values of x for which the polynomial is 0. Following the prescription, this equation is already set in standard form with a equals 1, b equals 0, and c equals 1. When we replace the values of a, b, and c in the variables to obtain x1 and x2, we can see that a square root of a negative number is involved. Now there is a problem, since there is not a real number that multiplied by itself gives minus 4. So we have reached an impasse, since we have not found the solutions to the equation, but the fundamental theorem of algebra tells us that there are 2 solutions. Is this theorem wrong? The answer is no. The fundamental theorem of algebra is not wrong. It is that we have not yet defined the complex numbers, and it will not be in these tutorials where I will do so, but the fact is that we can say that in this case there are no values of x in the real numbers that satisfy the equation. So we conclude that the polynomial x squared plus 1 has no real roots. That is equivalent to saying that there are no real values of x where the equation satisfies x squared plus 1 equals 0. So in summary, if you have a quadratic equation of the form a times x squared plus b times x plus c equal to 0 with a different from 0 and x, a, b, and c real numbers, the solutions to this equation are in general given by minus b plus minus the square root of b squared minus 4 times a times c with all that expression divided by 2 times a. Now, we have seen that in some cases there are no solutions, so we want an easy method to determine if there are any solutions, to not bother making all the calculations. And there is a way, but let's first define what the discriminant is. The discriminant of the quadratic equation is defined as the b squared minus 4 times a times c term. And this term will determine the properties of the solutions. If the discriminant is greater than 0, the quadratic equation has two solutions. If the discriminant is negative, then there are no real solutions. If the discriminant is 0, then there is one real solution. However, for the latter case, there is an important caveat. We say that there is only one solution since there is no other number that satisfies the equation, as the formula indicates. But the fundamental theorem of algebra tells us that there has to be two solutions. It turns out that there are two solutions, but they appear as the same. So we say that if the discriminant of the quadratic equation is equal to 0, there is a twofold degenerate root with whatever value minus b divided by 2a yields. And of course, in our context, most of the times we will not be interested in counting the solution twice if the discriminant is 0. But it is more an important technicality to discuss in case we come across a problem where we need both values. We will now take a look at algebra using multiple variables, since in physics you will have to use many variables at the same time. Now the advantage is that most of the things you have learned about single variables can be extended to multiple variables. In this tutorial though, I will only be focusing on linear equations since this topic is very broad and a whole year could be devoted to this kind of systems. Even more, once you get the hang of linear equations with two variables, you should be able to extend this to any number of variables you want and make the problems as complicated as you like. So in the previous cases, we had a single variable and a single equation whose solutions we wanted to find. In the case of multiple variables, we need as much equations as variables to uniquely determine the values of these variables. And by uniquely, I mean a finite number of consistent solutions to the problem, since there can be more than one solution to a set of equations. But there are sometimes more variables than equations, so there is not enough information to uniquely determine all the variables. There is also the case in which we have more equations than variables. That means we have an excess of information or inconsistent information, the latter being the most likely case. So let's start with the simplest example. Assume that we have two variables, call them x and y, and they are related through the equation 9x minus 2y equals minus 5. And we want to find all the pairs x and y that satisfy this equation. To solve the equation, we begin by counting the number of variables and equations. It turns out that there are two variables and one equation. The question is, can we find a unique solution to this equation? This is the dilemma that we find in the first case that we mentioned, about having more variables than equations. So let's explore how x and y are related to each other. To explore how x and y are related, let's make a table of how x and y behave when we choose several values of x. Now, before making the table, let's rearrange the equation such that we have y isolated on one side of the equation. And when we rearrange the formula, we now get that y is related to x by the equation y equals 9x plus 5 and everything divided by 2. We now choose several values of x and substitute them into the equation, and as we can see, the value of y will depend on the value of x chosen. So we say that y is a function of x. It could have been the other way around, but most of the time y is given as a function of x, and x is called the independent variable, since we can take any value of x within the real numbers, and y is called the dependent variable since, well, it depends on the value that x takes. In this case, we make the table of x and y. And we notice that, and this is the important part, that if we take any pair of these values and substitute them into the equation, 9x minus 2y, they will always yield minus 5. And these are just the values we chose because there are an infinite number of values that we have not considered. So there is no unique or finite number of solutions to the problem, as we had already expected. Let's look at another example. In this case, we have two equations. 9x minus 3y equals 5 and 6x plus y equals minus 2. And we want to find what values of x and y satisfy these two equations simultaneously. That is, if we take x and y and we substitute them into the first equation, the left side of the equation should yield 5, and if we substitute the same values of x and y into the second equation, the left-hand side should yield an answer of minus 2. So, as in the previous case, let's count the number of variables and equations. And if we do so, we find that there are two variables and two equations. So let's start with a graphical exploration of the problem. And as we did with the quadratic equation, we choose some values of x for the first equation and solve for y such that we get some points and plot them in a graph. And we do the same for the second equation with some different values of x than for the first equation, and we also get the values of y. And again, we plot them on the same axis as we did for the first equation. Now, in our case, the orange crosses represent the points obtained from the 6x plus y equals minus 2 relation, and the blue circles represent the 9x minus 3y equals 5 relation. But this is not very helpful since we cannot really see any values of x and y that yield the same values for both equations. However, we can draw some lines that pass through the points, joining them in a straight line so that we get the approximate ideal line from choosing an infinite number of points. And now we can find a point where there is a unique value of x and y that satisfy both equations at the same time. This point is exactly where the lines cross. And now it is difficult to see, but this point corresponds to values of roughly x equals to negative 0.03 and y equals to, again, roughly minus 1.75. Notice that if you replace these values of x and y in the first equation, they will yield approximately 5, and if you replace them in the second equation, they will yield approximately minus 2. But these estimates are not very useful if we are working on a calculation that requires, high accuracy. So can we get an exact solution? We now want to get an exact solution to the previous problem. That is, of course, more precise than the graphical approach. So the first step to solving the equation is to assume that both equations are independent and that they have nothing to do with each other. So the first equation we can use a 1 subscript on both x and y, and the same for the second equation by using 2 as a subscript. And we want to see any common value x1 equals to x2 and we want to see any common. So we determined that the value of x for which the two curves cross is x equal to minus 1 divided by 27. And the value for y can be determined from either equation by replacing the value of x. Again, the procedure is quite lengthy, and even if just one equation is needed, I show how it can be obtained with both equations, obtaining that y takes the value minus 16/9. So we conclude that the values of x and y that satisfy the two equations simultaneously are x equals to minus 1/27 and y equals minus 16/9. That, when compared to the values we got with the graphical analysis, are pretty close. But just consider that graphical methods only serve as an aid to determine and verify the exact values of the solutions. Let's give another example. Suppose that you have two relations in the form of equations. And as we did for the previous examples, we want to find the values of x and y that satisfy these equations simultaneously. We can again count the number of variables and equations we have, and according to what we discussed, we have two variables and two equations, so there must be a solution to the problem. So let's try to find the exact solution to the problem. And as the first step, we solve y for the first equation so that y is 2x minus 3, and as we did in the previous problem, we replace y into the second equation and we proceed to solve the equation to solve for x. But wait, have we done something wrong? Why is the result telling us that 6 is equal to minus 1? Does this make any sense? Just to see what is happening, we solve for y in both equations. And at this point, it may look obvious what is happening, but let's use some graphical exploration to see what's going on. So even if you already knew it, it turns out that the lines described by these equations are parallel, and well, parallel lines never intersect. Thus, we can conclude that there are no unique values of x and y that satisfy both equations simultaneously. And at this point, it should be clear that the result we obtain, 6 equals minus 1, just means that if there are any intersection points for these two equations, it is when the so-called y-axis intercepts are the same, meaning that there would only be effectively one equation, a case that we have already explored. So again, notice that at this point, you should be realizing that when you write out a number, it is exactly the same as writing, say, a letter. In other words, the use of numerical characters to represent a quantity is no different than using alphabetic characters. It is just the everyday notion that we have about using numbers that really hinders our understanding of algebra. So let's take a look at yet another example. Assume that now we have three equations, and once again, we ask ourselves, are there any unique solutions to these equations? So we count the number of equations and the number of variables, and we now have two variables and three equations. And we want to look now for an exact solution. And I'm not going to go into the details on how to solve these equations. So say if we use the first two equations to do this, or the last two equations, or the first and the last equations, they all yield the same value for x and y. So to solve this system, we have too much information. But how so? The equations look so different, and the relations between the equations are at least not obvious at first sight. The best approach we can take to make sense of what's happening is by plotting the lines. We can see that they are by no means parallel, but they intersect at the same point. Even more, if you multiply the first equation by 2 and then add it to the second one term by term, it turns out that this yields the third equation. And in this case, we say that one of the equations in the system is a linear combination of the other two equations. So as long as the third equation, or however more equations, is a linear combination of the other two equations, the solutions for the system are the same. And this is a property of these linear systems that are studied in linear algebra. Now, there are, of course, other cases, but so far we have worked with straight lines or linear equations, or equations of two variables where the variables are raised to the power of 1. But can these methods be extended to other kind of relations? Say, for example, to higher order polynomials or to other relations that are more complicated? The answer is yes, but it can be either easy, hard, or even impossible to find the point or the points where these relations satisfy the equations or equalities. So just remember that the rule of thumb is that for at least attempting to find a solution, the number of variables and equations have to be the same, or have more equations than variables, but being careful about inconsistencies or excess of information. And these are other examples of equations that appear commonly in physics, and some of them can be easily solved, like the intersection points of a line with a second-order polynomial, shown on the left, or the intersection points of a second-order polynomial with an exponential relation, shown on the right. And by the way, these points are kind of difficult to get. So to conclude and summarize, to find a finite number and uniquely determine the values of the variables that satisfy a number of equality relations, there must be as much equations as variables, although no solution is guaranteed to exist. If you have less equations than variables, then you cannot determine the variables uniquely, and the best you can do is to express the excess of variables in the form of an equation. And if you have more equations than variables, a solution might exist, but you have to be careful about excess information or inconsistencies. So this concludes this section on solving algebraic equations. We are now going to look at inequalities. Finally, I want to talk somewhat about inequalities, and this topic can also be somewhat extensive, but I at least want to give the basic properties of inequalities. So inequalities give a range of values instead of giving specific points, and there are four symbols that represent inequality relations. These symbols are called the greater than symbol, and is represented by an open triangle sign where the open part is facing the left. The greater than or equal sign is the same as the greater than sign, but it has a line under it. Then the less than sign is an inverted greater sign or an open triangle sign with the open part pointing to the right, and the less than or equal sign that is the same as the less than sign, but it has a line under it. And these are the inequality signs. Now, for example, we can represent the statements with inequalities. So 7 is greater than 5, 10 is greater than or equal to -3, 1 is less than 4, 6 is less than or equal to 6. But now you say, well, what about using inequalities and unknown variables? And these inequalities do exist and do have meanings. So for example, x greater than 7 means that x takes all the numbers greater than 7, not including 7. X greater than or equal to 10 means that x takes all the numbers greater than 10, including 10. X less than -1 means x takes all the numbers less than -1, not including -1. And x less than or equal to 0 means that x takes all the numbers less than 0, including 0. Inequalities can also be combined. For example, 4 less than or equal to x that is less than 10 means that x takes all the values that are in the range 4 to 10, but including 4 and not including 10. X less than 3 and x greater than or equal to 8 means that x takes all the values less than 3, not including 3, and x also takes the values greater than 8, including 8. Now, with these 6 cases, there are no more cases to consider, since this will be either redundant or inconsistent. It is important to notice that diagrams can be drawn to illustrate all of these cases. For example, let's take the first case where x is greater than 7. To start, we draw a line that represents the values that x can take with equally spaced intervals for consecutive and equally spaced values of x, including the value 7. Then, at the value 7, draw a hollow dot, here represented by a white dot, since we are not including the value 7, and highlight the sector of values that are greater than 7. In this case, represented by the red color. In this case, when using the greater than or equal sign, instead of using a white dot, we use a black dot since we are including the number 10. The other steps are followed in an analogous way. For the other two cases, we proceed as the first two, but now considering that x takes values that are less than a certain quantity. X greater than or equal to 4 and less than 10 is represented with a red line that connects the 4 and the 10, with a black dot on the 4 since it is included, and a hollow or white dot over the 10 since it is not included. In this case, the correct diagram to represent the inequality x is less than 3 and x is greater than or equal to 8 is by drawing the 2 points as shown and setting a black dot on the 8 mark since it is included, and a red line going towards the right, and a hollow or white dot on the 3 since it is not included, and a red line going towards the left. Of course, you can continue to combine these inequalities to define different intervals on the same set of numbers. Now, before I go into the last part of inequalities and the tutorial, I want to give some properties of inequalities and the real numbers. Of course, there are some more, but you can easily figure them out. So, assume that x, a, b, and c are real numbers. If a is greater than or equal to b, multiplying both sides by -1 flips the sign of the inequality. If a is greater than or equal to b, if you add or subtract any value c to both sides, it is guaranteed that the inequality will still hold. If a is greater than or equal to b, and you multiply both sides by any constant c that is greater than 0, the inequality will still hold. If a is greater than or equal to b, and both values different from 0, and both values have the same sign, either positive or negative, if the reciprocal of these values is taken, the inequality flips. If a is less than or equal to x, that is less than or equal to b, adding any constant c to all of the values a, b, and x, the inequalities will still hold. And if a is less than or equal to x and is less than or equal to b, multiplying all the values by a positive value c will not flip the sign of the inequalities. And these last two properties can be easily deduced from the first three properties. Finally, I just want to make a few remarks about inequalities with one or more variables and their meaning, with a few examples of inequalities with two unknowns. So inequalities with one or more unknown variables are useful to represent different sections. Inequalities of one variable are used to represent segments of lines. Inequalities of two variables represent patches of surfaces. Inequalities of three or more unknowns represent chunks of volumes. And inequalities of four or more variables represent pieces of hypervolumes. Examples for two unknown variables may represent simple rectangular areas. So, for example, this shaded rectangular area represents the inequalities -2 is less than or equal to x, that is less than 3, and 2 is less than or equal to y, that is less than 3. Notice that at the edges of the surface there are solid lines and dashed lines. The solid lines indicate the limit of the boundary that is included, and the dashed line also indicates the limit of the boundary. However, in this case, the boundary is not included. You can also represent more complicated sections like areas between curves, providing ranges. A simple case is that of -1 less than or equal to x and less than 7 and y greater than x. This results in the shaded area in the graph on the left. So if you take any point in the shaded area, you will see that any value of y is greater than x. Just be careful to notice that the dashed lines are not included. Of course, more complicated relations can be expressed like circular areas that would be represented by the inequality square root of x squared plus y squared is less than 5, where x and y can take any real value. This is represented by the figure on the right. Of course, this can get as complicated as you want. Okay, so we have reached the end of this tutorial, and as a summary, in this tutorial we have learned about algebra. In particular, we learned how to solve for x in a simple equation. We also learned how to solve the quadratic equation by using the quadratic formula and interpreting the possible outcomes of the number of solutions based on the value of the discriminant. We also learned how to solve linear equations of two or more unknowns by using substitution, along with the use of graphical exploration to verify or at least find the approximate values of the unique solution to the problem, if any at all. We also learned that to at least attempt to find a unique solution or solutions, we need to have as much variables as equations. If we have less equations than variables, all we can achieve is to express the excess of variables in terms of an equation. If there are as much equations as variables, there might be a finite number of solutions. If there are more equations than variables, there is either too much information or the relations are inconsistent, the latter being the most usual case. Of course, this can be extended to nonlinear equality relations, but most of the times it is really hard or even impossible. And we also learned about inequalities, some of the properties of inequalities, and how to represent regions in 1 and 2 dimensions, at least a few of the most basic ones. And well, I hope that you enjoyed and learned from this tutorial, and I hope to be uploading the remaining math tutorials in the next weeks. If you liked the video, please give it a like and subscribe to get the notifications for when the new videos come. So see you in the next video. Bye bye.